Yes.
Okay, good. All right, go ahead. It's your turn. You have
Please,
12 minutes to go and 3 minutes for the
can you
questions
tell
and
me?
answers.
Can you tell me if you can see my screen
We
right
see,
now?
we see it, yes.
Okay, I've decided to name my paper as Noise, the Path Towards Change, and it is on the behalf of the 18th anniversary of the history of noise written by Leon Cohen. Since we were kids, since in our early days, we have always been urged to make things simpler. We are often asked, why do you make or why do you complicate things? Growing up with this perspective, it was hard to create models to fit complex real life actions into easier versions. However, it took someone who appreciated the importance of observing things in detail to see the beauty in the complexity and understand that at some point we have to deal with these simplifications because real life doesn't work in a straightforward way. That person was Einstein. It was 1905, the miracle year, when he published four papers that served as breakthrough in science. It was the second time that Annus Mirabilis, or differently, the miracle year, was used for scientists, after it was used for the year 1666 related to Isaac Newton's works about discoveries in motion. In this year, Einstein published four papers. The first one on a heuristic point of view concerning the production and transformation of light. The second one on the electrodynamics of moving bodies. Does the inertia of a body depend upon its energy content? When he created the famous formula E equals squared. And also on the movement of small particles suspended in stationary liquids required by the molecular kinetic theory of heat. The paper that we are most interested in it is the investigations on the theory of the Brownian movement. In this paper, he observed and concluded experiments related to the Brownian motion in three key points. The osmotic pressure explained from the molecular kinetic theory of heat, the diffusion of small spheres in suspension, as well as the irregular movements of particles. In this paper, he made fascinating discoveries. He was able to express the diffusion coefficient in terms of well-known constants. As we can see in the formula, D represents the diffusion coefficient, R represents the gas constant, N represents the Avogadro's number, T represents the temperature of the system in Kelvin degrees, and P represents the radius of the particle we are taking into observation. But before that, he was able to find the Avogadro's number, which he denoted as N, but this number was later on named this way by Perry. And lastly, he concluded in this paper the fact that the kinetic energy of pollen matches the kinetic energy of atoms, proving that the movement of pollen is caused from atomic particles. Also, it was Brown who obtained many experiments and also concluded that the movement of pollen was not dependent on any current of the fluid or evaporation of the liquid. Throughout his work, Einstein derived very important stochastic concepts from the need to use them in his findings. Thus, he derived the Wiener-Knight theorem, which shows the relation between power spectrum and autocorrelation function in two papers. The first paper, a method for the statistical use of observations of apparently irregular quasi-periodic processes, and the second one, method for the determination of statistical values of observation regarding quantities subject to regular observation. He also utilized the autocorrelation function, represented it as a method to obtain statistical data concerning function f for observation. And this autocorrelation function, he managed to relate it with the spectral intensity shown in the formula below, which he denoted as Ix. Many experiments were held and many arguments were done related to the existence of atoms, but it was the work of many scientists that was used to solidly prove the existence of atoms, or as referred to the paper by Mr. Cohen as the little balls. So here we discussed about the discovery credited to Bernoulli. Bernoulli was inspired by Bohl's work, which stated that air exerts pressure that is inversely proportional to its volume. So Bernoulli concluded in this way that the pressure caused by gases is due to the force that atoms exert when they hit the side. This is how Boyle's law was derived. On the other hand, Lavoisier played an important role with his finding in chemistry. first proving that fire and water consist of oxygen and finding out that elements interact in mass proportions in chemical reactions. It was important to prove that water and fire exist because of oxygen in order to oppose the philosophical idea that was that time of five elements, that everything consists of five main elements: fire, water, earth, air, and a hypothetical element known as ether. Also, Dalton found the reason why substances react in mass proportion, and Clausius explained the temperature from the atomic viewpoint. All of these prove the existence of atoms. The discovery of atoms gave rise to other questions, also focused on the atomic interactions. At this point, it was able to be concluded that atoms collide together, what takes them more time to go from one point to another. So it was Clausius that got interested on the time that it takes a molecule before it is part of a collision. And also Maxwell found out that atoms have a variety of velocities from 0 to infinity, but distributed in a Gaussian distribution or Maxwell distribution. But why Gaussian or Maxwellian? Boltzmann also asked this question, also with two other important questions, which were what is the distribution in case of existence of internal or external force, as well as how does it evolve to a Maxwellian. We found out that the answer to all these questions were the atomic collisions. So in the equation I've shown in the slides, the right part of the equation shows the term depending on the collision. So at the end, he understood that the answer to all these questions is found at collisions, making this equation irreversible. In all of the previous slides, we have discussed that how some stochastic formulas were derived indirectly throughout the work to discover the existence of atoms. So it was Paul Langevin in 1908 with a paper on the theory of Brownian motion, who is often credited as the birth of stochastic differential equation. He had his own approach. He utilized Newton's equation to derive Stokes' law that in every atom moving in a liquid there exists a frictional force proportional to its velocity and correlated to its size and viscosity of the fluid. So he represented a force x considering the regular motion of particles in a liquid. And he made some mathematical manipulation and the important substitution shown in this equation. This substitution is related with the fundamentals to the equipartition of energy. At the end, he was able to express standard deviation with the formula that we know, also related to only well-known constants in that time. But besides Langevin, it was also the Fokker-Planck method. As we discussed earlier, Langevin method utilized the Newton's law and considered the stochastic force as any other force. He assumed that everything was deterministic. He also assumed that the mean of the forces was zero. In general, he provided fast calculations for specific moments, but as a disadvantage, it didn't calculate the probability distribution. This method also had an integral representation by Doob, in order to avoid the problem that the utilization of the second derivative to find a solution for xt which had no second derivative. Meanwhile, Fokker-Planck method wrote a differential equation for probability distribution with respect to velocity, position, or both. There exist some methods to go from one representation to another, such as Kramers-Moyal, Chapman-Enskog expansion, as well as master equations. And now that we have talked about stochasticity, it's time to talk about the most important topic in the scope of our course, which is noise. Noise can be found in different places as discussed as follows. For example, in stock market, Bachelor is known as one of the originator of stochastic processes, and he studied stock market behavior in probabilistic point of view, and he was able to derive the fundamental of stochastic processes. He derived the idea of transitive property of probability distribution shown in the equation above. Also, we can found noise in electrical engineering, where at that time important discoveries were made, such as Maxwell equation, which helped us to understand the magnetism and electricity, Gibbs method, which utilized matrix representation and made easier calculations, Hertz's discovery, which was a proof of existence of electromagnetic waves represented in Maxwell's equation, as well as Maxwell's light definition that light was an electromagnetic wave. And the most important one, it was the Edison's invention light bulb, which led to creation of generators divided in two types, AC and DC, DC of Edison and AC of Westinghouse. In electrical engineering, advancements were made in the technology. Wireless, created by Marconi, telephone, and also transatlantic cables. But everything was based on the conception found in the Edison creation of light bulb, the thermionic emission, which states that current can flow from the hot filament to a positively charged plate, even if they are not in contact. But it was De Forest who utilized this idea and made it better by creating the vacuum tubes, but added a grid in between as shown in the picture. Meanwhile, in electronics engineering, noise was first taken into consideration by Schottky, which also made important discoveries such as Schottky diodes, Schottky effect, as well as Schottky barrier. Shot noise was the kind of noise which is described as fluctuations around the average current distribution. It comes from the erratic movement of atoms going from the hot filament to the positively charged plate that we discussed earlier. And nowadays, this kind of noise is referred to any stochastic process that is sum of discrete events. On the other hand, we add thermal noise, which was created because of existence of loose electrons in the conductor, but electrons perform erratic movement whose sum was when no voltage was applied was zero. But when voltage is applied, it may happen that electrons may move in a certain direction. In good tube amplifiers that were produced later, thermal noise is one of the causes of most fluctuations. And the last one, it was the quantum noise, who gave rise to a different perspective to everything. Quantum theory explains in a different perspective the nature of matter from atom to the source of energy of the sun. It gave rise to quantum mechanics, which is based on the probabilistic point of view. It utilized the probability derived from the wave functions as well as analogous probability used in classical mechanics. And because of quantum theory, it gives rise to the specific and different kind of noise known as quantum noise. This noise was able to create a generalization of Langevin and Fokker-Planck's equation known as derived in here, where mm, the term denoted in the square, it is the 0 point noise fluctuation known as 0 point energy. Thank you.
Excellent presentation. Very good work. Any questions?